Hello my friends, welcome back to my channel. I hope you all are doing well and in a good health. So now I would demonstrate you about the design and simulation of the notch filter in this video. So as we know that we have seen the video about the low pass and high pass and band pass filters. So basically there is a fourth type of filter as well, which is known as band stop filter. The notch filter is an advanced version of the band stop filter actually. So the band stop filter is basically the one is a circuit which blocks a particular band of frequencies, uh, a wide band of frequencies or a mid band of frequencies, and it passes the rest of the frequencies in the spectrum. Okay, whereas the notch filter is the um, advanced version of the band stop filter in which the bandwidth is narrow and it has a higher attenuation at a very narrow or steep notch of the frequency band or frequency spectrum. So basically a band pass filter, band stop filter is a type of frequency selective circuit that has an exact opposite functionality to the band pass filter. As the name itself indicates, that it will stop or attenuate a particular band or range of frequencies. Since it eliminates frequencies, so it is also known as a band reject filter or band elimination filter. Also, the eliminated frequencies, known as the stop band of the filter. The band stop filter is formed by the combination of the low pass and the high pass filter connected in parallel with each other through an amplifier circuit. We all know that an amplifier circuit is required in order to process the low voltage signals into a higher, relatively millivolt level of signals to be processed by the analog to digital converter in the following circuit. So the amplifier circuit I'm not going to discuss in this video, but I would show you how to design the notch filter. Unlike the high pass and low pass filters, the band stop filters and the band pass filters also have two cutoff frequencies. It will pass above or below a particular range of frequencies, whose cutoff frequencies are defined by the components used in the circuit. Any frequency that is in between these cutoff frequencies is attenuated. So basically the notch filter is also a band stop filter. The notch created by the notch filter is very narrow and the frequencies are highly attenuated over a few hertz. And also I would also want to mention here that the highly selective term means the high value of Q. As we know that Q is the ratio of the center frequency and the bandwidth. So in most of the band stop filters, the value of Q is not very high, but in notch filter the value of Q is high. Okay, so now we will be going to see the design and simulation of the notch filter. Okay, so guys, I have already calculated the notch filter design for you guys, so you can easily see which formulas are being used in the notch filter designing. So the configuration of the notch 20 notch filter is something like this. As you can see here that we have two T's, two T configurations, that is why it is known as 20. This R1 and this R2 and this capacitor C. This is the low pass filter, and it makes 1T, whereas this capacitor C2 and this capacitor C3 and this resistor R3 makes the high pass filter, which is second T, and these T are connected with each other in parallel configuration, as you can see. Okay, so it makes this circuit as 20 notch filter. So now we consider the notch frequency to be 1 kilohertz, and the 3 dB cutoff frequencies would be at 100 hertz bandwidth, that is 100 hertz plus 1000 hertz, that is 1.1 kilohertz, and 1000 hertz minus 100 hertz, that is 900 hertz. So our frequencies ranging in between 900 hertz and 1100 hertz would be attenuated, and the rest of the spectrum of the frequencies would be passing through the circuit from in to the out. We would perform this simulation in LTSpice after we see the formulas and calculation of notch filter. Okay, so here is the formula of the notch filter frequency, that is 1 upon 4 pi RC, and this R is actually the value of resistors being used here, and this C is the value of capacitor being used in these capacitors. As you can see, the low pass filter capacitance is twice of that of the high pass filter capacitance C, and the resistor being used in the low pass filter is also twice of that of the resistor being used in the high pass filter. Okay, so as soon as we know these R and C values, we would know all these component values as well. So let's first of all consider C to be equals to 0.1 microfarad, that is 100 nanofarad. This is the most common value of capacitors being used in the filter circuits. So now let's calculate value of R. So by rearranging the formula, we get R something like this. So we put the values and we get value of R to be equal to 795 ohm, or we can say it is 800 ohms. Okay, so now we have the value of R and value of C. So we, in other words, know all the values of the components. Now let's come on to the value of Q. The Q factor is basically the ratio of the notch frequency to the bandwidth, as I have already mentioned. So put the values of the frequency and bandwidth, so we get the value of Q factor value equals to 10, which is very high, by the way. Normally we get the value of Q's in 1 or 2's or under root 2, but this Q value 10 is very high, and which is the specialty of the notch filter. So now let's move on to the circuit design. But before going to the simulation circuit design, the one thing which is left is the feedback factor. This feedback factor is basically the output signal being fed into the input circuitry at some particular ratio. And this I would show you in the simulation. When we are going to simulate the circuit, I would show you this feedback factor, but for now just see the formula, that is the feedback factor K is equals to 1 minus 1 upon 4Q, and we got the value of Q, so we will get the value of K as well. And as I have said that the output signal ratio is fed back into the input, therefore that ratio is considered using the voltage divider resistor, which we would see in the simulation circuit design. The value of K is basically the voltage divider resistor voltages, that is the voltage across R4 and sum of R3 plus R4. R3.5. Okay, so basically here the last thing, which is the notch depth. How we would know that the attenuation value of a particular frequency which is being attenuated, that is in our case is 1 kilohertz. So the attenuation value is calculated from the value of q here. Q, the value of q here is equals to 10. So the value of 1 upon q would be equals to 0.1. Therefore this 0.1 here comes from 1 upon q. So the value of the notch depth is basically 20 times the log of 1 upon q. Then we would get minus 20 dB attenuation at 1 kilohertz. We would see these attenuation and cutoff frequencies in the simulation. Okay, let's move on to the simulation. Okay, so now guys, I have quickly assembled all the components on the LTSpice schematic, and we can start here. So you can see this circuit is the same as I have mentioned in the calculations and formulas details. So we calculated our resistor to be equal to 795 ohm. So I would simply replace the value of resistor here, 795, or we can place 800 ohm resistor for sake of simplicity. And now twice of the same resistor would be 795 multiplied to 1590. Okay, and our this capacitor was 0.1 microfarad, and we assume our capacitor to be 0.1 microfarad. Therefore twice of the capacitor would be 0.2 microfarad. So actually basically this is the passive type of notch filter, in which we do not have any feedback from output into the input, as I will show you next. So now let's simulate the circuit. So we see what we get on the output node with this simulation analysis. As you know, this is the AC analysis, and I have started from frequency 1 hertz up to the 10 kilohertz frequency signal, and with the type of decade, sweep type is decade. Okay, so let's see this. As you can see, we have got a very beautiful notch, but not very steep although. Okay, so now I would show you very precisely. Let's make this frequency, starting frequency from left, to be equals to 100 hertz. So we will now see the frequency ranging from 100 hertz to 10 kilohertz instead of from 1 hertz to 10 kilohertz. Okay, now as you can see here, now I would place the cursor 1 on 3 dB points. This is basically the point where our cutoff is lying. As you can see here, it is 0 dB, and up to minus 3 dB it is, as you can see here, 2.96, and here is 3 dB. Now I would place another cursor 2 on the minus 3 dB cutoff frequency on the upper side of the spectrum, and here as you can see it is also at exactly minus 3.0 here. So you can see here the two cutoffs, that is at cursor 1 lower cutoff and cursor 2 is the higher cutoff, and our center frequency is 1 kilohertz, which is the notch frequency basically. So our notch frequency is exactly 1 kilohertz as we see in our calculation, but our bandwidth is very wide, as you can see in the passive design of this 20 notch filter. The difference between the two cutoffs is around 4.01 kilohertz, which is not very good. We need to have a cut bandwidth of around 100 hertz. But basically, as you can see, the attenuation is around minus 63 dBs, minus 63 dB attenuation. The depth of the attenuation notch is at minus 63 dB, and this is basically not required as well. We do not need such a deep frequency attenuation. We only needed 20 dB attenuation, but with a steep and squeezed notch spectrum. Okay, so let's see where is our 900 hertz line. As you can see here, this is the frequency, the lower cutoff frequency. This is the lower cutoff frequency, which is at cursor 1. Okay, so this is changing. This is the lower cutoff frequency, and I will show you where is our lower cutoff frequency lying 900 hertz, which was to be around calculation 900 hertz here. And this is our upper cutoff frequency, which was around supposed to be 1.1 kilohertz. So all the way down here 1.1 here. As you can see, it is 1.1 kilohertz now, and it is 900 hertz. So as you can see, the bandwidth is still at 209 hertz, or we can assume 200 hertz, and the magnitudes are minus 25 dBs, which is again not as we expected or not as we calculated. We expected the magnitude to be around 20 dB, not minus 25, not so much attenuated, only 20 dB, minus 20 dB attenuation, and our bandwidth to be equals to 100 hertz. So here it means that all the frequencies that is above this frequency have attenuation less than minus 25, and here it is also here is a minus 20 dB. As you can see, the attenuation is now at minus 20 dB. If we increase our attenuation to minus 20 dB, now as you can see, it is around minus 20 dB. But you see here our bandwidth increased around twice, from 200 hertz to 400 hertz. So we need to fix these things. We need to fix this thing. We need to squeeze this stop band, this notch band, this notch. Okay, so now what I would do here, I would use an op-amp. I would use an op-amp. I would include the SPICE directive of OPA 1656. As we all know that OPA 1656 is a dual op-amp and is very perfect for the audio filter circuits. So I would use an op-amp model from here. Op-amp, I would use op-amp 2, because op-amp 2 has the option to include the SPICE model from your computer or laptop directory. I have this computer and laptop directory path which I had already copied from my computer. Now I would also place power supply for the op-amp, that is dual plus minus 15 volt. So this battery here 15 volt and minus 15 volt, I would connect them in series to get our VCC and VW, right? I would place the ground here. Okay, and I would rename this value to OPA 1656. This is very important, and I have already already mentioned this in my previous video that you have to change this name to this name, this op1656.lib. You don't need to include extension .lib here. Only here you need to include the extension .lib. Okay, so now we would simply delete this wire here, and we would simply connect this input at positive, and we connect the VCC to positive VCC and negative VE to negative. I have found this non-inverting buffer configuration of op-amp, and this would enable us to have our attenuation controlled at -20 dB level. Okay, so now we would be using another part of this OPS 1656 second op-amp into the feedback to feedback the output signal into the input circuitry. For this we need to delete this ground connection and copy this op-amp and place those resistors which we calculated previously. Place ground here. These are the voltage divider resistors which we calculated previously. 10K, 250R. Connect to the output, and this is fed back into the input circuitry. This is the main filter circuit, and this negative pin is basically the non-inverting buffer amplifier configuration, which you can say. Now place the VCC, VEE. Okay, it's done now. Let's simulate again the circuit and see what happens. Okay, great. As you can see now, the response is much steeper and much squeezed notch, as you can see clearly. This is much beautiful response as compared to our previous passive version of the 20 notch filter. Now again we start to analyze from 100 Hz, and we can see here at 1 kilohertz, exactly at 1 kilohertz, and our lower cutoff is standing at 900 Hz, as you can see here, 900 Hz, and another cutoff is at 1.1 kilohertz. Okay, as you can see at -3 dB, at -3 dBs cutoffs, we have our bandwidth equal to exactly 100 Hz, and our frequencies are almost at 900 Hz and 1.1 kilohertz. So this is basically 950 Hz and 1050 Hz instead of 1100 Hz, which is much better and which is much steeper and much squeezy notch response. Okay guys, as you can see here, and you can also see that the phase is also at 90 degrees, -90, exactly at -90 at 1 kilohertz. So that is it guys. uh, if you guys have any questions, then just let me know, and I would be here again with another video, hopefully for the band stop filter. Although the notch filter covered the band stop filter, but I would like to make a small video about band stop filter circuit and its response. Okay friends, I hope this you enjoyed this long video, and I thank you for your patience to be with me on this video till the end. Thank you very much. Keep good, take care of yourself. Thank you. Bye bye.